Hey there, Algebra 2. We are in Chapter 4, Section 3. What is the title of this one? Sorry, I don't actually know off the top of my head. There we go. Use functions involving e. All right, let's get into it, and you guys will understand what e is. All right, warm up. Let's review some important information. Simplify expressions. If you remember, these are all, goodness, exponents. They didn't come out very well. But when you have x to the first and x to the fifth, it becomes x to the 1 minus 5. Oh gosh, that's 12th. Sorry, that's x to the 12th. 12 minus 5. Then you have y to the third and y to the negative third minus a negative 3. And then 21 over 45, you just need to simplify. Okay, 21 over 5, or 45, it looks like you can put 3 into there. So you have 7 over 15. And then your variables, 12 minus 5 is 7. So x to the 7th power. 3 minus negative 3 is y to the 6th power. So there you have it simplified. Minus the 45. There we go. Power to a power, let me rewrite this so it's a little bit clearer. Negative 2, a to the 3rd power, b to the 2nd power, all raised to the 4th power. You distribute that, negative 2 to the 4th power, a to the 3 times 4, and b to the 2 times 4. Negative 2 to the 4th power, let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16. That's an even number, so we have a positive 16. A to the 12th and b to the 8th is our answer. Those are really important exponent rules that you need to know. Oh gosh, that's terrible formatting. It's a cubed root of 64, r to the 9th, s to the 6th, t to the 3rd. So cubed root of 64 is 4. Then you have r to the 9th raised to the 3rd power because it's cubed roots. That'd be r to the 3rd power. S to the 6th to the 3rd power. That is s squared. And then t to the 3rd power. So the 1/3 power is t. Cool? All right, an account with a balance of $1,000 pays 3.65 annual interest compounded daily. What is the balance at the end of 1 year if no money is added to the principal? That's where we have 1 plus r over n. So 0.0365. We're compounding daily, so 365 raised to the 365 times 1. And I need a calculator. Hold on. You do all that math and you get $1,037.17. All right, let's get into the new lesson. This concept, the development of E, which is Euler's number, pronounced Euler. I know, I have no idea why, but whatever. The concept is actually difficult to explain, but let's look at this. The history of mathematics is marked by the discovery of special numbers such as pi and I. We know that pi is an irrational number, 3.14, etc., etc., etc. I is another irrational number, which is the square root of -1. Another special number is denoted by the letter E. The number is called the natural base E, or the Euler number, after its discoverer, Leonhard Euler, who lived a long time ago. The expression 1 plus 1 over n raised to the n approaches E, which is a number, as n increases. So if we look at it, if n is equal to 10 to the first power and you plug it into here, you get this number. If n is equal to 10 to the second power and you plug it into this formula, you get this number. Again, n is this, plug it in, you get that. And you see we're approaching a certain number. N is equal to this, and it's very, very big. You plug it in, you get this number. N gets bigger and bigger. Okay? This number right here, as n gets bigger and bigger and bigger, this number converges to what they're calling the number e, which is, if you type your calculator, if you find the E button and hit enter, it'll give you an irrational number that never ends, 2.7182, etc., etc., etc. Okay? So let's look. The definition, the natural base E. The natural base E is irrational. It is defined as follows. As n approaches infinity, this formula approaches 2.7182, etc., etc., etc. Okay? It's an irrational number. Why? That is saved for future math classes. Let's use it though. First, let's just do the math with it. Simplify the expression. E to the second power times e to the fifth power. Okay, this is my base. Because my base is the same, I can add my exponents. Just like if it were an x. Oops. Sorry. Okay. Just like if it were an x to the second, an x to the fifth, you add the exponents. Okay, same here. I have 12 e to the fourth power over 3 e to the third power. If I take the numbers, 12 divided by 3 is 4. E to the 4 over e to the 3 is 4 minus 3. Gives me 4e. Okay, here, let me rewrite it so you can see it. 5e to the negative 3x. That whole thing squared. I distribute that squared and I get 5 squared. E to the negative 3x times 2 gives me 25 e to the negative 6x, which is 25, oh gosh, I've lost all space. You guys catching all this? Okay, so I have 5 squared times e to the negative 3x times 2, which is 25 e to the negative 6x, which is 25 over e to the 6x. When you're simplifying, you want no negative exponents. All right, calculator to evaluate expressions. I don't know why my formatting is such a mess. So this is e to the fourth. So if you're typing this into your calculator, you're going to hit the second button and the e to the x button. It's along the left-hand side of your calculator. So second, e to the x, and 4. So what you'll see in your calculator is e to the fourth. And then hit enter. And you get this. Gosh, why am I rewriting it, right? Okay, this is e to the negative 0.09. So in your calculator, you will type e, which is second, e to the x, and then negative 0.09, and then hit enter. And you get 0.91, etc., etc. Okay? I will gladly show you where that is when you're doing your homework. Just yell and I'll come running. All right, guided practice. So I have e to the 7th times e to the 4th, e to the 7 plus 4, e to the 11th. These are the same. I'll rewrite them so we can see them. 2 times e to the negative 3rd times 6 times e to the 5th. I take those coefficients in the front, multiply them, and I have negative 3 plus 5, 12 e to the 2nd. Okay, my numbers divide, I get 6, and then e to the 8th minus 5, 6 e to the 3rd power. Simplify the expression, I'll rewrite it so we can see it. E to the negative 4x to the 3rd power gives me 10 to the 3rd power. E to the negative 4x times 3, which is 3 zeros over e to the 12x, because this right here is negative 12x, so it drops to the denominator. Use a calculator to evaluate e raised to the 3/4. You might want to do e exponent 3/4. I'll double check that it works. And that 3/4, just use your division button and you get the right answer, which is 2.117, lots of zeros. 1, 2, 3, 4, 1, 7. Cool? Cool. All right, when we graph a function of the form y equals a times e to the x is called a natural base exponential function. If a is greater than 0 and r is greater than 0, the function is growth. If a is greater than 0 and r is less than 0, it is decay. The graphs of the basic functions y equals e to the x and y equals e to the negative x are shown. Sorry about this. That should not be there. But this would be exponential, which is y equals e to the x. Please notice that it crosses the y-axis at 0, 1, and then 1, e. So my points are 0, 1, and 1, e, which is 2.718, right? Here we have e to the negative x, which crosses the y-axis 0, 1, and also gives me the point 1, 0.368. This right here is e to the negative 1. Okay, if you just go to your calculator and type in e to the negative 1, you get 0.367879, etc., etc. And that would be your e to the negative x, right? So let's try one. Graph the function. Y equals 3e to the 0.25x. So I can say my first point is 0, 3. The second point is 1, 3 times e to the 0.25. So this gives me 0, 3 and 1, if I do this math right here, I get 3.85, which we see those 2 points graphed right there. We know it's growth, so we're good. Draw your curve. Our domain does say state the domain. The domain is going to be all real numbers, and the range is y is greater than 0. Okay, let's try another one. This gives me y equals e to the negative 0.75, x minus 2, plus 1. Now these act just like our exponential growth and decay, where this is h equals 2. So we're moving to the right 2. And this right here is k equals 1. So I'm moving up 1. So I will graph the parent function, y equals e to the negative 0.75x. So I have 0, 1 and 1, I need to raise e to the negative 0.75, which is 0.47. As we can see there, the 1, 0.47 is not quite as useful. Let's see, I'll get a blue pen. So if I actually plugged in 0, 1 is good, but we have a negative 2. If I plug in negative 2 for x, I get e to the negative 0.75 times 2. I mean negative 2. So e to the negative 0.75 times negative 2. And that gives me 4.48, which is a little easier to graph. You could have used the 1, 0.47. Negative 2 just gave me a little bit more room to graph with. So my points are 0, 1 right there, and negative 2, 4.48, which is pretty close to 4.5. And now we're going to translate. I'm moving right 2 and up 1. So 1, 2, up 1, put a dot, and right 2, up 1, put a dot. And that's how we get our translated curve of decay because we're negative. Okay, my domain is all real numbers, and my range is y is greater than 1, which we get from this point right here. All right, moving on. Example 4, biology. The length L in centimeters of a tiger shark can be modeled by the function L equals 337 minus 276 times e to the negative 1.78t. Let me rewrite that so it looks better. L equals 337 minus 276 times e to the negative 0.178 t, where t is the shark's age in years. Graph the model. Use the graph to estimate the length of a tiger shark that is 3 years old. Okay? If we look, I went to my handy dandy calculator and graphed the model as shown. Y equals, I typed this into y-1, 337 minus 276 e to the negative 0.178 t. And you can go ahead, if you look, you can use x, okay? It's right next to the t in your function. So I'll rewrite that just so you can see it. When I typed it in x right there. Okay, and then I hit the graph button. It was hard for me to see this graph because if you look at x equals 3, y equals 175. So I'm going to hit my window and change my scale. So for x, I'm going to go from 0, I don't know. So for x, my min is 0, my max is, I don't know, 10. And my scale is 1. For my y's, I'm going to go from 0 to, I don't know, let's try 200 and see how it works. So 0 to 200. I'm going to change my y scale SCL to 10, just so we're not going by ones. Then I hit graph again, and it looks pretty close to this. It's pretty cool. Okay. If I hit the trace button, just look for the trace button, and I trace over to x equals 3, like it shows, still scrolling, I can get to x equals 2.978 and x equals 3.085. I can't get to exactly 3. But for that, my y equals 174.5. Y equals 177.6. So we're going to go for y equals 175. And that's the estimate of the length of a tiger shark when they're 3 years old. Okay, so 175 centimeters. All right, try a few. Graph the function, state the domain and range. Y equals 2 times e to 0.5x. That means I can say 0, 2 and 1, I'm going to go ahead and type in e to the 0.5 times that by 2, and I have 3. So 0, 2 is right there, and 1, 3.3, which is right there. It's growth. Domain equals all real numbers. Range equals, range, y is greater than 0. Here we have y equals 1/2 e to the negative x plus 1. So this right here, k is up 1. I don't have an h, so I'm not moving left or right any. My parent function is y equals 1/2 e to the negative x. So I can graph 0, 1/2 and 1, I'm going to type in e to the negative 1, multiply that by 0.5 or 1/2, and I get 0.18. Not easy to graph, which if you remember in the lesson part, we graphed like a -2 to get this value up here. So let's go ahead and try that. If I plug in -2, so I have e to the -2 times that by 0.5. That doesn't help. E to the -2. Oh, sorry. I typed it in wrong. Let's try that one more time. E to the -2, which is just 2, times 0.5 gives me, there we go, 3.69. So -2, 1, 2, 3.69. All right, so I'm going to erase this because I need to graph the parent function first. I'm going to highlight the parent function in black. So 0, 1/2 is about right there. And -2, 3.69. So -2, 1, 2, 3.69 is about right there. Now we're just going up 1. We're not going left or right any. So I'll go in red. I just go up 1, about right there. Up 1 is about right there. That is how, in fact, I get that graph. Okay, it works quite well. Let me redraw this. Y equals 1.5 e to the 0.25 x minus 1. And then the whole thing should be -2. So here I have h equals 1, which is a right one. K equals -2. So down 2. Let's go ahead and graph our parent function, which is 1.5 e to the 0.25x. That gives me 0, 1.5 and 1, I'm going to do e to the 0.25, enter, times 1.5, 1 to the 1.9. So if I graph that in black and then shift it right 1 and down 2, so 0, 1.5 and 1, 1.9, and then we're going to go right 1 and down 2. So how do I want to do this? Right 1 down 2. Right 1 down 2. Oh, stink. Their scale is wrong. Sorry, their scale is different, not wrong. So let me try this again. So sorry. First, I'm going to go ahead and graph these in blue. Okay, 0, 1.5. So 0, 1.5 is right there. And 1, 1.9, 1.9 is just below 2. Now I'm going to do this in red. Right 1, down 2. So right 1 is just half of a block, and down 2 is 1, 2. That makes better sense because these go by 2s. Now this one is right 1, down 1, 2. Okay, and then we have our curve. Okay, that not cool when they change their scale like that. All right, what if in example 4, use the, I need example 4 again, sorry. There we go. Use the given function to estimate the length of a tiger shark that is 5 years old. So I'm doing length. I'm just going to go ahead and type it in, like calculate it. E to the negative 0.178 times t. So I have, first I need to calculate this. So I've got 276 times e, parentheses, negative 0.178 times 5, close your parentheses. So that right there gives me 113.3. 337 minus my answer. This gives me 223.7 centimeters. Check my answer. Yep, they got 224 centimeters. So did I. So fun. All right, moving on. Continuously compounded interest. This right here is more common than what we've done in the past. You've learned that the balance of an account earning compound interest is given by this formula. This is when we're compounding in certain time periods. As the frequency n of compounding approaches positive infinity, the compound interest formula approaches the following formula. Oh, so sorry. I need to pay better attention. When interest is compounded continuously, the amount A in an account after t years is given by the formula. A equals P e to the RT. I call this the A-PERT. A equals P times e to the RT, where P is the principal, R is the annual interest rate expressed as a decimal. Cool? Let's try one. You deposit $4,000 in an account that pays 6% annual interest, compounded continuously. What is the balance after 1 year? So we have our principal equals 4,000. Our rate is 0.06 and our time is 1. So the balance after 1 year is 4,000 e to the 0.06 times 1 You type that into your calculator, you get approximately $4,247.35. Pretty cool. Okay, A PERT, very important. A equals P to the ERT. Finance. You deposit $2,500 in an account that pays 5% annual interest compounded continuously. Find the balance after each amount of time. So, 2,500 e to the 0.05 times 2. 2,500. I have to calculate, I know. E to the 0.05 times 5. 2,500 e to the 0.05 times 7.5. Go ahead and calculate them. I am doing the same. 0.05 times 2. I get $2,762.93. This is the same problem for 5 years. I have $3,210.06. Same problem, 7.5 years. Gives me $3,637.48. Cool. The amount of interest earned in parts A through C of exercise 10. It's an interesting way. So just the interest. If our principal that we started out with was $2,500, in part A, we had 2762.93, B 3210.06, C 3637.48. So I'm just going to take those numbers and subtract 2,500. Yeah. So my interest earned is $262.93. My next one is, hold on, I went backwards. Sorry. So I take the 3,210 and subtract 2,500, and I get $710.06. That's pretty good. Now this last one's going to be the best, right? I earned $1,137.48. That's pretty good, right? That's how much I earned. Daily homework quiz, we made it. Okay, these are hard to read. So this would be e to the x times e to the negative 3x, all of that squared. Okay, this would be e to the negative 0.35. Y equals, I'm sorry, I don't know how this happened. 2 e to the 0.3 times x minus 5 plus 3. That's why y is greater than 3, and domain is always all real numbers. There we go. That's it. You're done. Nice work. Good job.